The Sun's core burns at 27 million degrees Fahrenheit. Yet the average temperature of space hovers just 3 degrees above absolute zero. The floor of the universe, a temperature nothing has ever actually touched. This is not a contradiction, it is a clue. Temperature requires matter to exist, the jostling of atoms, the vibration of molecules, and space has almost none. A vacuum holds no heat and no cold in the conventional sense. The question itself barely makes sense. The Sun pours out more energy every second than humanity has used in all of recorded history. Yet that torrent crosses 93 million miles of nothing without warming the void. Warmth, it turns out, is not the default state of the cosmos. It is the exception. Tonight's question sounds like a paradox. The Sun's core burns at 27 million degrees Fahrenheit, yet step beyond Earth's atmosphere, and the void hovers just 3 degrees above the coldest temperature physically possible. The contradiction dissolves once the physics are laid bare. Temperature requires matter to exist, and space has almost none. Before we begin the journey from the surface of the Sun to the coldest natural place ever found, leave a comment with your city and the time right now. And if you haven't already, subscribe to Sleep Among Galaxies for more slow cosmic questions answered in the dark. The warmth we take for granted is the rarest thing in the cosmos. The Sun's core burns at 15 million degrees Celsius. At that depth, hydrogen nuclei collide and fuse under pressures no laboratory on Earth has ever sustained, and the temperature climbs so high that matter exists only as plasma, a state where electrons have been torn free and atoms cease to exist in any recognizable form. The energy released in a single second exceeds all the power humanity has consumed across the entirety of recorded history. That furnace has been burning for 4.5 billion years, and it will continue for another 5 billion more, steady and indifferent. Move outward from the core, through layers of convective churning where columns of plasma rise and fall like slow tides, and the temperature drops. The surface of the Sun, the photosphere, glows at roughly 5,500 degrees Celsius. This is the layer we see when we look up during the day, the brilliant disk that casts shadows and warms skin and makes life possible. It is cooler than the interior by millions of degrees, yet still hot enough to vaporize any material we know. But climb higher still, into the corona, the Sun's outer halo, and something strange happens. The temperature surges again, rising to between 1 and 3 million degrees Celsius. The corona burns hotter than the surface itself, a puzzle scientists still debate. Magnetic fields twist and snap in the thin plasma, releasing energy in bursts that defy simple explanation. The Sun, even in its outermost reaches, remains a furnace. And yet, just beyond that halo, the temperature plummets. Space, the void that begins where the corona fades, hovers at an average temperature of 2.725 Kelvin. That is roughly minus 270 degrees Celsius, or minus 454 degrees Fahrenheit. It is a measurement taken not from matter, but from the faint microwave radiation that fills every corner of the universe, a relic of the early cosmos still traveling, still cooling. This temperature sits just 2 3/4 degrees above absolute zero, the floor of the universe, a temperature nothing has ever actually touched. The paradox settles in slowly. The Sun radiates more energy than entire civilizations could ever harness, yet the space surrounding it, the space through which that energy travels, remains colder than any winter night on Earth, colder than the deepest Antarctic ice, colder than anything the human body can survive unprotected. The distance between the Sun and the void is not measured in millions of miles, it is measured in inches. The corona gives way to the vacuum, without ceremony, without transition, without boundary. One moment, plasma at 1,000,000 degrees. The next, near absolute cold. This is not a failure of the Sun's power. The sun's energy crosses 93 million miles of nothing in 8 minutes, carried not by any substance but by light itself. Photons stream outward in every direction, a torrent of electromagnetic radiation that does not slow, does not cool, does not require a medium to travel through. The light arrives at Earth still potent enough to warm oceans, drive weather, sustain every living thing. But the space it crosses remains untouched. The void does not absorb the heat, it simply allows the light to pass. The paradox is not that space is cold, the paradox is that space has no temperature at all, not in the way a freezer or a winter wind has temperature. A freezer chills through air pressing against skin, molecules colliding and stealing heat. Space has nothing to press against anything. It is not cold in the sense of pulling warmth away. It is cold in the sense of absence. Temperature requires matter to exist, and in a vacuum the question itself barely makes sense. The 2.725 Kelvin measurement is not the temperature of space itself. It is the temperature of the cosmic microwave background, the oldest light in the universe, a faint afterglow filling every point in the observable cosmos. This radiation was released roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely for the first time. At that moment, the temperature was around 3000 Kelvin, hot enough to glow a dull red. The universe has been cooling for 13.8 billion years, and it is not finished. The expansion of space stretches the wavelengths of that ancient light, shifting it from visible to infrared to microwave, lowering its temperature degree by degree across eons. What we measure today is the echo of a much hotter beginning, still present, still uniform, still fading into silence. The sun and the void coexist without contradiction, because temperature, in its most fundamental sense, is a property of matter. It measures the average kinetic energy of particles in motion, atoms jostling and colliding, transferring momentum. In a vacuum, there are almost no particles. There is nothing to jostle. A cubic meter of interstellar space might contain only a handful of hydrogen atoms, drifting alone, separated by distances greater than the width of a human hand. The question of temperature in such a place loses its grip on meaning. The sun is hot because it is dense with matter, particles slamming together at unimaginable speeds. Space is cold because it is empty, a near-perfect vacuum where the ordinary rules of heat transfer dissolve. The corona paradox sharpens the picture. The sun's surface, crowded with particles, sits at 5,500 degrees. The corona, far less dense, burns 1,000 times hotter. The explanation most scientists favor involves magnetic reconnection, the sudden release of energy stored in twisted magnetic field lines that thread through the plasma, like invisible cables under tension. But the details remain unsettled, the models incomplete. The corona is a reminder that heat and density do not always move in step, that the physics of plasma and magnetism can defy intuition. The sun's outer atmosphere, tenuous and ghostly, reaches temperatures that would vaporize any known material, yet it exerts almost no force. An astronaut could pass through the corona and feel nothing, not because it is not hot, but because there is not enough matter to transfer that heat. The energy is there. The medium to carry it is not. This is the central paradox. The sun is a furnace. Space is a void. They touch, and neither changes the other. The sun does not warm space. Space does not cool the sun. They exist in parallel, governed by different rules, separated not by distance but by the presence or absence of matter. The sun radiates, space receives. And the temperature of the void remains, as it has for billions of years, just shy of the coldest temperature the universe allows. The paradox extends outward beyond our solar system, into the larger architecture of the cosmos. The thin gas threading between galaxies can reach millions of degrees, heated by shockwaves from colliding galaxy clusters, yet it is so sparse it would register as a near-perfect vacuum in any laboratory on Earth. A single cloud of gas, a nebula where stars are born, can hold pockets of 10,000 degrees and pockets of nearly absolute zero, separated by vast distances within the same structure. The cosmos does not sort itself neatly into hot and cold. It layers them, interweaves them, holds them in tension across scales that dwarf comprehension. And somewhere, far from any star, a dying sun exhales. The Boomerang Nebula, 5,000 light-years away, is the coldest natural place we have ever found. A star in its final stages ejects gas so fast, the expansion chills it below the temperature of the cosmic microwave background itself, down to roughly 1 Kelvin. The gas rushes outward at hundreds of thousands of miles per hour, and in doing so, it cools below the background of space, colder than the void, colder than the ancient light that fills the universe. It is a reminder that the universe's baseline is not the coldest it can be. There are mechanisms, rare and fleeting, that can push matter even closer to absolute zero, closer to the floor nothing has ever touched. The sun burns at 15 million degrees at its core, 5,500 at its surface, and up to 3 million in its corona. Space, beginning just beyond that corona, hovers at 2.725 Kelvin. The gap is not a contradiction, it is a consequence. Heat belongs to matter. The void is the absence of matter. And the universe, in its vastness, is overwhelmingly void. The sun is an island of warmth in an ocean of cold, and the ocean does not care. It does not conduct. It does not convect. It simply waits, patient and indifferent, as the light passes through. The paradox holds. Across every scale the universe offers, a reminder that warmth is not the default state of existence. It is the exception, the rare gathering of matter and energy in configurations delicate enough to sustain it. The sun burns, the void waits, and between them no bridge exists. Temperature is not what it feels like. It is not the sting of ice on fingertips or the flush of heat across skin. It is something more fundamental, something that exists only where matter exists. Temperature is the measure of motion at the smallest scale, the jittering, colliding dance of atoms and molecules, each one carrying kinetic energy as it tumbles through space. The faster they move, the hotter the substance. The slower, the colder. Strip away the motion entirely, and what remains is absolute zero, the floor of the universe, a temperature nothing has ever actually touched. This definition holds true in a kitchen, in a star, in the heart of a nebula. But it falters in the void. Space is not filled with atoms bouncing against one another. It is almost perfectly empty. A handful of hydrogen atoms scattered across a volume the size of a cathedral. In such a place, the question of temperature begins to dissolve. Temperature requires matter to exist. In a vacuum, the question itself barely makes sense. Consider the difference between a freezer and the void. A freezer chills through contact. Air molecules press against skin, stealing heat through conduction. The cold is transferred particle by particle, a cascade of energy flowing from warm to cool. The air itself becomes the medium of the chill, a substance dense enough to carry kinetic energy away. Space offers no such contact. There is nothing to press against anything. An object adrift in the vacuum does not freeze the way a hand freezes in winter. It simply radiates its own heat away, slowly, into the dark, with nothing to replace it, and no surrounding medium to conduct the cold inward. The background temperature often cited for space, 2.725 degrees above absolute zero, is not the temperature of matter, it is the temperature of light. The cosmic microwave background, the faint afterglow of the early universe, fills every corner of space. It is radiation, not substance. photons left over from a time when the cosmos was young and hot, now stretched and cooled by billions of years of expansion. These photons do carry a temperature, but they do not conduct it. They do not press against anything. They simply pass through, a whisper of warmth in a place that has no medium to hold warmth. A thermometer placed in the void would not read the temperature of space. It would read its own temperature, the balance between the radiation it absorbs and the radiation it emits. If sunlight strikes it, the thermometer warms. If it drifts into shadow, it cools. But the space around it has not changed. The void itself remains what it has always been, a near-total absence of matter, and therefore a near-total absence of the conditions that allow temperature to exist in the familiar sense. The thermometer floats in a place where temperature, as a property of the environment, has almost no meaning. What it measures is only itself, and the light that happens to fall upon it. The sun floods the solar system with energy. More energy every second than humanity has used in all of recorded history. A torrent of radiation pouring outward in all directions, enough to ignite atmospheres, melt rock, sustain oceans. Yet this torrent crosses 93 million miles of nothing without warming the vacuum itself. The energy travels as radiation. Electromagnetic waves that require no medium, no air, no substance to carry them. Light itself is the messenger. It departs the sun's surface at 10,000 degrees Fahrenheit, crosses the void in 8 minutes, and arrives at Earth, still carrying that energy, undiminished by the emptiness it passed through. The vacuum has not absorbed it. The vacuum has not been warmed by it. The vacuum has simply allowed it to pass. An astronaut floating in low Earth orbit experiences this directly. Exposed metal on a spacecraft can reach 250 degrees Fahrenheit in direct sunlight. Step into shadow, and the same surface drops to roughly minus 250 degrees. The swing is more than 300 degrees, and it happens in seconds, on the same body. 16 sunrises every single day, 16 full swings between furnace and freezer. The spacesuit that protects against this cycle is a marvel of insulation. 18 layers, a network of water-cooled tubes against the skin, all designed to manage a range that would kill in minutes without it. The body inside remains stable, held at a narrow band of warmth by technology that must simultaneously block the flood of radiation from the sun and prevent the body's own heat from radiating away into the void. Yet the space around the astronaut has not changed temperature. The void remains as it was. What changes is the radiation field, the presence or absence of sunlight, the only mechanism of heat transfer that functions across a vacuum. Conduction requires matter. Convection requires matter. Radiation does not. It is the lone carrier of energy in a place where almost nothing else exists. The astronaut is warmed or chilled, not by the space itself, but by the light passing through it, and by the absence of light when shadow falls. The universe is filled with extremes that illustrate this paradox. The corona of the sun burns 1,000 times hotter than the surface below it, reaching temperatures in the millions of degrees. The mechanism is still debated. Magnetic reconnection, waves of energy cascading through plasma, but the fact remains. The outer halo of the sun is hotter than the layers beneath, a puzzle that reminds us that temperature and proximity do not always align. Elsewhere, nebulae hold pockets of gas at 10,000 degrees, ionized by the light of newborn stars, and pockets of nearly absolute zero in the cold molecular cloud cores where stars have not yet formed. The same cloud, separated by vast distances, contains both extremes. A nursery of future stars, holding regions of furnace heat and regions of near-total stillness, each one defined by the density of matter and the presence or absence of radiation. The thin gas threading between galaxies can reach millions of degrees in the halos of galaxy clusters, yet it is so sparse it would register as a near-perfect vacuum in any laboratory on Earth. Temperature without substance. Heat without the matter to carry it in the way we understand heat on the surface of a planet. The coldest natural place ever found is not in the depths of intergalactic space. It is the Boomerang Nebula, a dying star exhaling gas so fast the expansion chills it below the background temperature of the cosmos itself. 1 degree above absolute zero, colder than the faint microwave glow that fills the universe. A pocket of extreme cold carved out by motion, by the physics of adiabatic cooling, in a place where the usual rules of warmth and cold barely apply. The gas rushes outward, expands, and in expanding loses energy, chills, falls below even the ancient light that bathes the rest of space. It is a reminder that cold, like heat, is not a substance. It is the absence of motion, the slowing of particles, the withdrawal of kinetic energy until almost nothing remains. And yet, for all these extremes, the overwhelming majority of the universe is neither hot nor cold in any meaningful sense. It is empty, dark, silent. The voids between galaxy filaments, the gulfs between stars, the space that makes up most of the volume of the observable cosmos, these places hold almost no matter, almost no particles to carry kinetic energy, almost no temperature to measure. A traveler passing through such a place would find no air to freeze them, no surface to burn them, no medium to conduct warmth or cold, only the faint pressure of starlight from distant suns, and the even fainter glow of the cosmic microwave background, a signal so weak it barely registers as anything at all. Temperature, in the end, is a property of things, of atoms jostling in a gas, of molecules vibrating in a solid, of plasma roiling in the heart of a star. Where there are no things, there is no temperature. Only the faint background hum of ancient light, cooling slowly, as the universe expands and the distances grow and the matter that does exist drifts farther and farther apart. The microwave background itself is cooling, has been cooling for nearly 14 billion years, and will continue to cool as space stretches, and the photons lose energy to the expansion. The universe was once hot enough to glow, now it barely whispers. The paradox dissolves once this is understood. The sun is not heating space. It is heating the objects within space. Planets, moons, dust grains, anything with matter to absorb radiation and convert it to kinetic energy. The void itself remains untouched. A vacuum has no temperature in the conventional sense. It is not cold the way ice is cold. It is simply absent. Heat moves in 3 ways. Each one tells a different story about why space feels the way it does, and why the sun's fire does not fill the void around it. The first is conduction. Touch a metal spoon left in a hot pan, and the heat flows directly into your hand, molecule to molecule, atom to atom, each one jostling its neighbor until the energy spreads. Conduction requires contact. It requires matter pressed close enough for particles to collide, to pass their motion along like a whisper traveling through a crowd. In the vacuum between worlds, there is no crowd. There is almost nothing at all. Conduction cannot happen where there is nothing to conduct. Strip away the matter and the chain breaks. The heat has nowhere to go, no path to follow, no neighbor to nudge. In space, conduction is not merely difficult, it is impossible. The second is convection. Warm air rises from a radiator, cool air sinks, and the room fills with circulating currents that carry heat from one place to another. Convection is the bulk movement of fluids and gases, the stirring of matter in motion. It is how oceans distribute warmth across a planet, how the atmosphere smooths out the temperature between day and night, how a pot of water begins to churn as heat spreads from bottom to top. But convection, like conduction, requires matter. It requires a medium that can flow, that can carry energy in its movement, that can rise when warmed and sink when cooled. Space has no such medium. There is no air to rise, no water to churn, no substance to carry heat from the sun outward into the dark. The void does not circulate. It does not stir. It simply stretches, empty and still, offering no pathway for warmth to spread. The third mechanism is radiation. It is the only one that works across a vacuum. Radiation is heat carried not by particles but by light itself, by electromagnetic waves that need no medium, no substance, no bridge. Infrared, visible light, ultraviolet, all of them rippling outward from the sun at the speed of light, crossing the void without touching anything, without needing anything to exist between source and destination. The sun's energy crosses 93 million miles of nothing in 8 minutes, carried not by any substance but by light itself. Radiation does not ask for matter. It does not require a chain of collisions or a fluid to stir. It simply moves, wave after wave, through emptiness as easily as through air, indifferent to the absence that surrounds it. This is why space can be so cold when the sun is so hot. 2 of the 3 pathways are closed. The heat of the sun cannot conduct into the void because there is nothing to conduct through. It cannot convect because there is no fluid to stir, no gas to rise and fall. It can only radiate, and radiation moves in straight lines, spreading outward in all directions, thinning as it goes, a sphere of light, expanding into an ocean of emptiness. The farther the light travels, the more it spreads, the more diluted it becomes. By the time it reaches the outer edges of the solar system, the same sunlight that warms Earth has thinned to a pale glimmer, barely enough to heat a surface above the background cold. The sun emits more energy every second than humanity has used in all of recorded history. It pours that energy into space without pause, a torrent of light and heat flung outward at the speed of thought. And yet the vast majority of it never touches anything. It simply travels, spreading thinner and thinner, until it fades into the background glow that fills the universe, the faint whisper left over from the beginning of time. The energy is not lost. It is merely dispersed, scattered across distances so vast that it becomes indistinguishable from the oldest light in the universe, still traveling, still cooling. Stand in direct sunlight on Earth, and the warmth on skin is radiation. The sun's light crosses the void, strikes the atmosphere, filters through the air, and lands as heat. But the air is also warm, heated by conduction from the ground, stirred by convection into breezes and currents. A freezer chills through air pressing against skin. Space has nothing to press against anything. There is no air to carry the cold, no medium to conduct it. In space, cold is not a force. It is simply the absence of heat, and that absence is profound. An object in space, far from any star, receives almost no radiation. It floats in a sea of near-nothingness, and without conduction or convection to warm it, it cools until it matches the faint background glow of the universe itself. That glow is not warmth in any sense a human body would recognize. It is the thermal radiation left over from the early universe, filling every corner of space with a temperature barely above the floor of existence. The object does not freeze the way water freezes in a freezer. It simply radiates away whatever heat it once held, losing energy to the void, until there is almost nothing left to lose. But place that same object in direct sunlight and everything changes. Radiation floods one side, heating exposed metal to 250 degrees Fahrenheit or more. The other side, facing away from the sun, radiates its own heat into the void, and drops to roughly minus 250 degrees in shadow. There is no air to smooth the difference, no convection to stir the temperature into something uniform. The object becomes a study in extremes, one side baking, the other freezing, separated by nothing but a shadow. The transition is immediate. Step from light into darkness, and the temperature plummets, not gradually, but in seconds. An astronaut on a spacewalk experiences this directly. Step from sunlight into shadow, and the temperature swings more than 300 degrees in seconds on the same body. The suit compensates with 18 layers of insulation, a network of water-cooled tubes against the skin, systems designed to manage a range no natural environment on Earth could produce. The International Space Station orbits through 16 sunrises every single day, 16 full swings between furnace and freezer, a rhythm no living thing evolved to endure. Each orbit takes roughly 90 minutes. Each sunrise brings a flood of radiation. Each sunset brings a plunge into cold. The station does not experience weather. It experiences extremes, cycling endlessly between light and shadow, heat and void. Radiation is the only mechanism that survives in the void, and it creates a universe of islands. Wherever light falls, there is heat. Wherever shadow lies, there is cold. There is no gradient, no gentle transition, no medium to carry warmth from one place to another. Heat exists only where radiation strikes, and everywhere else the temperature drops toward the faint glow of the background itself, the hum that fills the space between stars. The universe is not a gradient from hot to cold. It is a collection of bright points surrounded by darkness, each one radiating into an emptiness that cannot hold the heat, cannot carry it, cannot soften it. This is not intuitive. On Earth, heat spreads. A fire warms a room. A hot stove heats the air. The sun warms the ground, and the ground warms the air, and the air circulates, until the whole atmosphere holds the heat, distributes it, softens the extremes. We live inside a blanket of matter, and that blanket conducts, convects, and holds heat close. We have never known a place where heat does not spread, where warmth does not fill the space around its source. Every environment we have ever encountered has been mediated by matter, by air or water or rock, by substances that carry heat and cold and smooth the transitions between them. But space is that place. It is a place where two of the three pathways are absent, where heat cannot spread because there is nothing to spread through. The sun burns at its core with a temperature beyond 15 million degrees, yet a few million miles away, in the space between planets, the temperature is defined only by how much radiation is intercepted and how much is radiated away in turn. There is no ambient temperature in the way we understand it. There is only the light that reaches an object, and the light it loses. The void does not have a temperature. It has an absence where temperature would be, if there were enough matter present to give the concept meaning. Radiation is patient. It does not need a medium. It does not need anything to exist between source and destination. It simply travels, crossing the void at the speed of light, carrying energy in waves that will warm whatever they eventually strike, if they strike anything at all. Most of the sun's light never does. It radiates outward into the dark, into the space between stars, and it travels for millions of years without touching a single atom, until it fades into the background, indistinguishable from the faint glow that has filled the universe since the beginning. This is the answer to the question. Space is cold not because the sun is weak, but because space is empty. Heat requires matter to exist, and the void has almost none. Conduction and convection are mechanisms of proximity, of substance, of worlds, where particles press close enough to share their motion. Radiation is the mechanism of distance, of light crossing emptiness, of warmth that exists only where it lands. The sun is hot. Space is not cold. Space is simply absent, and in that absence, heat becomes the rarest thing in the cosmos. An astronaut floats outside the International Space Station, tethered to a structure of aluminium and composite panels racing through the vacuum at 17,000 miles per hour. One side of the body faces the sun, the other faces the infinite dark. Between them, a difference of more than 300 degrees. In direct sunlight, exposed metal on the spacecraft can reach 250 degrees Fahrenheit. The sun's radiation strikes the surface with nothing to slow it, no atmosphere to scatter or soften the light. The metal absorbs the energy and heats until it glows faintly in the infrared. A hand placed against it would blister in seconds. The same handrail, warmed not by any surrounding medium but by photons that crossed 93 million miles of nothing in 8 minutes, and arrived with their full intensity intact. Step into shadow and the temperature plummets to roughly -250 degrees Fahrenheit. The same hand, the same glove, the same moment in time. The metal that was hot enough to burn now cools toward the background temperature of space itself. The swing happens in seconds, on the same body, across a distance shorter than the length of a human arm. No breeze chills the surface, no ice forms. The metal simply radiates its heat into the void as invisible light, and the void offers nothing in return. The astronaut does not freeze. The astronaut does not burn. Between skin and void lie 18 layers of insulation, a network of water-cooled tubes pressed against the torso and limbs, and a reflective outer shell that bounces most of the sun's energy back into space before it can conduct inward. The suit is not clothing. It is a portable atmosphere, a miniature Earth wrapped around a fragile body, maintaining a steady 70 degrees inside, while the outside oscillates between furnace and freezer every 45 minutes. The cooling garment clings to the skin, circulating water chilled by radiators mounted on the backpack. When the astronaut drifts into shadow, a small heater warms the water before it reaches the chest and limbs. The system runs without pause, balancing the extremes, erasing the 300-degree swings before they can reach flesh. The International Space Station completes one full orbit of Earth every 90 minutes. In that time, it passes through 16 sunrises and 16 sunsets. 16 full swings between light and shadow. 16 cycles of heating and cooling. The station's exterior is a patchwork of materials chosen not for strength alone, but for their ability to endure this endless whiplash. White paint reflects sunlight. Gold foil deflects infrared. Radiators extend like wings, shedding the heat generated by computers and humans and life support systems into the void, where it disperses as invisible light and never returns. This is the astronaut experience. Not the cold of space, but the absence of mediation. On Earth, air surrounds the body and conducts heat away when the skin grows too warm, or insulates when the air itself is cold. Water vapor rises and falls. Wind moves. The atmosphere is a buffer, a constant negotiator between the sun and the surface. In orbit, there is no buffer. Sunlight strikes with full intensity, or does not strike at all. There is no gradient, no twilight, no gentle transition. Only presence or absence. The line between them is sharp enough to cast shadows with edges like razors. The sun floods the void with more energy every second than humanity has used in all of recorded history. It radiates in every direction, a sphere of light expanding at 670 million miles per hour. Most of it travels into emptiness, and will continue traveling for billions of years without ever striking anything. A tiny fraction intercepts Earth. An even smaller fraction intercepts the space station. But that fraction is enough to heat metal to 250 degrees in minutes. The energy arrives not as warmth but as light, carried by photons that know no temperature, only momentum and wavelength. The energy arrives as light. Visible light, infrared, ultraviolet. Photons that left the sun's surface 8 minutes earlier, crossing the distance without losing speed or direction. They carry no heat in the way a warm breeze carries heat. They carry energy, and when they strike matter, that energy converts. The metal absorbs the photons, and its atoms vibrate faster. Temperature rises, but only where the light lands. A bolt in full sunlight can reach 250 degrees, while a bolt 10 centimeters away, shaded by a solar panel, sits at -250. The vacuum between them conducts nothing. The temperature difference persists, stable, unreconciled. Turn away from the sun and the atoms slow. The metal radiates its own infrared light back into the void, shedding energy in every direction. There is nothing to reflect it back, nothing to trap it, nothing to recycle it. The heat leaves and does not return. The surface cools toward the background, toward the 2.7-degree floor that fills every corner of space. In shadow, the station's hull approaches that floor within minutes, limited only by the faint warmth conducted through bolts and struts from the sunlit side, and the heat leaking outward from the pressurized modules within. An astronaut working on the exterior of the station moves carefully between sunlit panels and shadowed bays. The suit compensates. Water circulates through the cooling garment, drawing heat away from the skin and pumping it toward radiators on the suit's backpack. When the astronaut enters shadow, a heater activates, warming the water before it reaches the skin. The system runs continuously, balancing the extremes, maintaining the narrow range within which human tissue can survive. The astronaut feels neither the 250 degrees nor the -250. The astronaut feels 70 degrees, the same 70 degrees as inside the station, the same 70 degrees as a spring afternoon on Earth. But the suit is a temporary shelter. It carries enough oxygen for 7 hours, enough battery power for 8. The cooling system can fail. The insulation can tear. A puncture the size of a pinhole can depressurize the suit in minutes. The astronaut is not adapted to this environment. No amount of training changes the fact that a human body, unprotected, would lose consciousness in 15 seconds and cool by radiation alone, the slowest of the three mechanisms, shedding heat as infrared light into a void that absorbs everything and returns nothing. The space station orbits at the boundary between Earth's atmosphere and the true void. Below, air still clings to the planet, thick enough to scatter light and carry sound and hold warmth against the surface. Above, the density drops to near zero. A few stray atoms of hydrogen per cubic centimeter, not enough to conduct heat, not enough to convey temperature in any conventional sense. The vacuum does not freeze the station. The vacuum does not warm it. The vacuum does nothing. It is the sun that warms, and the absence of the sun that allows cooling. The station exists in a state of constant thermal negotiation, every surface either absorbing light or radiating heat. The balance maintained by design, by layers, by the deliberate arrangement of reflective foil and black radiators, and white thermal blankets. 16 times a day, the station crosses the terminator, the line between day and night, the edge where sunlight ends. From the perspective of an astronaut looking out a window, the transition is instant. One moment the Earth below is bright, clouds and oceans gleaming. The next moment, darkness. The station's exterior lights switch on. The radiators continue to glow faintly in infrared, invisible to the eye but visible to the cameras that monitor the station's thermal balance. The temperature on the sunlit side was 250 degrees. The temperature in shadow will reach -250 within minutes. The interior remains 70 degrees, unchanged, insulated from the swings by layers of foam and foil, and the constant hum of fans circulating air warmed by the heat of human bodies and machines. This is not the coldest place in the universe. Farther out, in the space between galaxies, the background temperature still holds at 2.7 degrees, undisturbed by any nearby star. But it is the place where humans have learned to live, Briefly, in the gap between the sun's furnace and the background's whisper, the place where the paradox is most tangible, where warmth and cold exist not as distant abstractions but as immediate, physical, mortal facts separated by the thickness of a glove, the astronaut finishes the task, re-enters the airlock, and waits for the pressure to equalize. The suit's cooling system winds down. The outer layers, scorched by sunlight and chilled by shadow, remain at their extreme temperatures for a few minutes longer before they too stabilize. Inside, the astronaut is warm, breathing recycled air, floating in a capsule of metal and fabric and carefully managed energy, a bubble of 70 degrees in a universe that averages nearly -460. Long before the first galaxies assembled their light, before stars had names or planets had orbits, the universe was a furnace. Not the kind that heats a room or melts metal, but a state so dense and so hot that matter itself could not hold together. Atoms could not form. Light could not travel. Everything that would one day become galaxies, stars, dust, and distant worlds was compressed into a roiling sea of particles and radiation, colliding endlessly in the dark. Then the universe began to expand, not into something, but as something. Space itself stretched, and as it stretched, it cooled, the furnace dimmed, the collision slowed. And roughly 380,000 years after the beginning, the temperature dropped just enough for electrons to bind to nuclei. Atoms formed. Light, which had been trapped in an endless scattering dance with free particles, was suddenly free to move. The universe became transparent. That first light, released all at once from every point in space, began a journey that has never ended. It is still traveling now. It fills the room where this voice is heard. It passes through the walls, through the air, through skin and bone. It bathes every star, every planet, every grain of dust floating between galaxies. It is the oldest light in the universe, and it is everywhere. Scientists call it the cosmic microwave background. It is not a place, it is not a thing. It is a faint afterglow filling every corner of space, the memory of a moment when the universe first learned to let go. When that light was released, it was hot. The universe at 380,000 years old was still glowing at roughly 3,000 degrees Kelvin, bright enough to cast shadows, hot enough to vaporize rock. But space has been expanding ever since, and as it expands, the light stretches with it. Wavelengths lengthen. Energy dilutes. The glow that once filled the cosmos with visible light has been pulled into the microwave range, invisible to human eyes, detectable only by instruments built to listen for whispers. Today, that ancient light carries a temperature of 2.725 Kelvin, not 2.725 degrees above freezing. 2.725 degrees above absolute zero, the floor of the universe, a temperature nothing has ever actually touched. It is colder than the surface of any planet. Colder than the darkest crater on the moon. Colder than the shadowed ice at the poles of Mercury. It is the baseline temperature of the cosmos, the background hum beneath everything else. This is not the cold of a winter night or a freezer. A freezer chills through air pressing against skin, through metal conducting heat away from flesh. The cosmic microwave background does neither. It is radiation, not matter. It does not touch. It does not press. It simply is. A field of low-energy photons washing over everything, carrying almost no warmth at all, yet defining the average temperature of the universe itself. Temperature requires matter to exist, particles in motion transferring energy through contact or flow. The cosmic microwave background is the temperature of photons, not of substance. It is what remains when there is nothing left to be warm. The discovery came by accident. In the spring of 1965, two scientists at Bell Laboratories in New Jersey were trying to eliminate noise from a radio antenna shaped like a giant horn. No matter how carefully they calibrated, No matter how many times they cleaned pigeon droppings from the metal, a faint hiss remained. It came from every direction. It never changed. It had no source they could identify. What they had found, without knowing it at first, was the echo of the Big Bang. Arno Penzias and Robert Wilson won the Nobel Prize 13 years later, not for seeking the origin of the universe, but for listening carefully to static. The signal they detected is still there. It has not faded. Satellites have mapped it in exquisite detail, charting tiny fluctuations in temperature across the sky, variations of a few millionths of a degree that mark the seeds of all structure in the cosmos. Those ripples, frozen into the light when the universe was a fraction of its current age, would one day grow into galaxy clusters, voids, filaments spanning hundreds of millions of light-years. But the background itself remains smooth, uniform, patient. It does not care what forms within it, it simply continues to cool. The universe has been cooling for 13.8 billion years, and it is not finished. At 380,000 years old, the temperature was 3000 Kelvin. Today it is 2.725. In another 100 billion years, it will be colder still. The expansion will not stop. The stretching will not reverse. Every passing moment pulls the wavelengths a little longer, drains a little more energy from the light. The cosmos is not approaching equilibrium. It is drifting slowly, inexorably, toward a state where even this faint glow will be too dim to measure, too cold to warm anything, too dispersed to gather. Yet for now, the cosmic microwave background is the warmest thing in most of space. Step away from a star, away from a planet, away from the faint heat of nebulae, or the thin gas threading between galaxies, and this is what remains. 2.725 Kelvin. A whisper of warmth in an ocean of nothing. It is the temperature of the void, the temperature of distance, the temperature of the universe when it has nothing else to offer. There are places colder than this. A dying star, thousands of light-years away, exhales gas so quickly that it chills below the background of space itself. The Boomerang Nebula, the coldest natural place ever found, sits at roughly 1 Kelvin, colder than the ancient light surrounding it. The star ejects materials so fast, with such force, that the expansion cools the gas faster than the cosmic microwave background can warm it. It is a fleeting exception, a local eddy in the slow current of cosmic cooling. The background does not compete, it does not vary, it simply waits, patient and even, while stars burn and die, while galaxies collide and drift apart, while warmth flares briefly in a universe that has no memory of heat. An astronaut floating in shadow far from the sun would not freeze instantly. There is no air to steal heat through convection, no surface to conduct it away, but the suit would begin to radiate warmth into the void, and the void would radiate back only this, 2.725 Kelvin, the faintest echo of a fire that went out billions of years before the first star ignited. The astronaut would not feel the cosmic microwave background. It is too weak, too diffuse. But it would be there, surrounding the body, filling the space between helmet and stars, a temperature so close to nothing that it barely registers as a number at all. Beneath the wild oscillation between furnace and freezer, the background remains constant, indifferent, 2.725 Kelvin in all directions. The sun pours energy into space at a rate beyond comprehension, more in a single second than humanity has used in all of recorded history. Yet the sun is a single point. Space is infinite in practice, endless in reach. The light spreads, thins, fades. By the time it crosses the orbit of Neptune, it is a pale glimmer. By the time it reaches the nearest star, it is lost in the background. And beyond the stars, beyond the galaxies, there is only this. The uniform glow of the beginning, stretched and cooled and spread so thin that it offers almost nothing. The cosmic microwave background is not a wall, it is not a barrier. It is a condition, the thermal state of a universe that has been expanding and cooling since the moment it began. It is the answer to the question of what temperature space has when there is no sun nearby, no planet, no nebula, no cluster of galaxies heating the thin gas between them. It is the temperature of everywhere and nowhere, the average of a cosmos too vast to warm. It is what fills the space between stars, when radiation from those stars has traveled too far to matter. It is what remains when every local source of heat has been subtracted, when distance has swallowed every flicker of warmth. And it is still falling. The universe will never stop expanding, barring discoveries that overturn everything currently understood. The background will continue to cool, asymptotically approaching zero but never reaching it, a descent without an endpoint. In 1 trillion years, galaxies will have drifted so far apart that most of the sky will be dark. The cosmic microwave background will still be there, colder than it is now, fainter, harder to detect, but present. It is the one thing that will outlast nearly everything else, the final light, the last warmth, the memory of a moment when the universe was young enough to glow. The light that was released 380,000 years after the beginning has now traveled for more than 13 billion years. It has crossed distances so vast that the galaxies it passes no longer resemble the galaxies it left behind. It has watched stars form and die, watched planets coalesce and freeze, watched entire clusters of galaxies merge and drift into the dark. And through it all, it has cooled. The photons that once carried the heat of a young universe now carry almost none. They have been stretched by the expansion of space itself, their energy diluted across an ever-growing volume, their temperature dropping degree by degree, century by century, eon by eon. For now it fills the space between words, between breaths, between thoughts. It is the temperature of the room when the sun is not shining, when the earth is not warming, when all the temporary fires have gone out. It is the baseline, the floor, the quiet hum beneath the cosmos. And it is all that most of space will ever know of warmth. The sun's surface glows at 5,500 degrees Celsius, a temperature that would vaporize iron in seconds. Yet just above that surface, stretching outward like a ghostly crown, the corona burns 1,000 times hotter than the surface below it, and no one has fully agreed on why. The leading explanation invokes magnetic fields that twist and snap, releasing stored energy in sudden bursts, but the physics remains contested. Here, within sight of the sun's visible edge, the universe refuses to follow the simple rule that heat flows from hot to cold. The corona is hotter than the furnace beneath it, and the mystery lingers in every solar eclipse photograph, in every spacecraft measurement, in every model that tries and fails to close the gap between observation and theory. This paradox is not unique to the sun. Temperature across the cosmos does not arrange itself in tidy gradients. It clusters in extremes, separated by voids that hold almost nothing at all. A nebula, the birthplace of stars, can harbor pockets of 10,000 degrees, where newborn light ionizes hydrogen, and pockets of nearly absolute zero, where molecular clouds drift in darkness, all within the same sprawling structure. The Orion Nebula, visible to the naked eye as a faint smudge beneath the Hunter's belt, contains both furnace and freezer, each occupying a volume larger than entire solar systems, each invisible to the other, across distances so vast that light takes years to cross them. The same cloud of gas, the same nursery of future stars, holds temperatures that span 4 orders of magnitude, and no single number can describe it. The transition is not gradual. It is abrupt, marked not by a gradient but by emptiness. by the absence of matter dense enough to carry heat from one zone to the next. Between galaxies, the thin gas threading the cosmic web can reach millions of degrees. Yet it is so sparse it would register as a near-perfect vacuum in any laboratory on Earth. This is the intergalactic medium, a plasma so diffuse that a single cubic meter might contain only a handful of atoms, yet so vast that it accounts for a significant fraction of the ordinary matter in the universe. In the halos of galaxy clusters, where gravity compresses this gas, temperatures climb higher still, driven not by stars, but by the sheer weight of matter falling inward. The gas glows in X-rays, invisible to human eyes, detectable only by space telescopes designed to see heat that has no substance to carry it. A thermometer placed in this medium would read millions of degrees. A hand placed in the same space would freeze, because there is nothing there to transfer the heat. Temperature and cold coexist, separated not by distance, but by the absence of matter itself. And then there is the Boomerang Nebula, 5,000 light-years away in the constellation Centaurus, where a dying star exhales so fast, the gas chills below the background of space itself, the coldest natural place we have ever found. The star at its center, nearing the end of its life, ejects material at hundreds of kilometers per second, and the expansion cools the gas faster than the universe can warm it. The temperature drops to 1 degree, above absolute zero, colder than the faint microwave glow that fills the rest of space, colder than any comet, any shadow, any void. This is not the product of distance from a star. It is the product of motion, of matter fleeing itself so quickly that thermal energy drains away faster than radiation can replenish it. The nebula appears as a faint hourglass in telescope images, pale and symmetrical, and within it the universe touches the floor of temperature, the limit where motion itself nearly stops. These zones, corona, nebula, intergalactic medium, dying star, share no common thread except contrast. Heat in the cosmos does not spread evenly. It concentrates in pockets, in shells, in filaments, each one surrounded by emptiness that holds no temperature at all in any conventional sense. The sun's core burns at 15 million degrees, yet a spacecraft in Earth's shadow, less than 100 million miles away, will cool to roughly 250 degrees below 0 Fahrenheit within minutes. The transition is not gradual. There is no medium to carry the gradient. Radiation crosses the void at the speed of light, but it does not warm the void itself. It warms only what it strikes, and most of space contains nothing to strike. An astronaut stepping from sunlight into shadow feels this divide immediately. The same body, the same suit, swings more than 300 degrees in seconds. 18 layers of insulation, a network of water-cooled tubes against the skin, and still the temperature differential is so extreme that every surface exposed to the sun must be designed to radiate heat, and every surface in shadow must be designed to retain it. The International Space Station experiences 16 sunrises every single day, 16 full swings between furnace and freezer, each one lasting only minutes. In direct sunlight, exposed metal on a spacecraft can reach 250 degrees Fahrenheit. In shadow, the same metal plunges to -250. The line between the two is sharp, visible, a boundary drawn by geometry rather than physics. Yet the station orbits within a region of relative warmth. It sits within the sun's influence, bathed in radiation strong enough to power solar panels, close enough that Earth itself glows in reflected light. Step beyond this bubble, beyond the orbit of Neptune, beyond the Kuiper belt, into the space between stars, and even this oscillation fades. The sun becomes a point of light no brighter than Venus appears from Earth. The background temperature settles toward the cosmic microwave background, that faint afterglow filling every corner of space, The oldest light in the universe still traveling, still cooling. At 2¾ degrees above absolute zero, this is the baseline, the temperature that matter reaches when it is far from any star, any galaxy, any source of energy, except the universe itself. But even this baseline is not uniform. The cosmic microwave background is smooth to within 1 part in 100,000, but the matter embedded in it is not. Dark matter filaments trace the large-scale structure of the universe, and where ordinary matter falls into these filaments, it heats. Where it remains in the voids between filaments, it cools. The universe is not a single temperature. It is a tapestry of temperatures, each one determined by local conditions: gravity, density, radiation, motion, and the overwhelming majority of that tapestry is cold, empty, and silent. Warmth, by contrast, requires coincidence. It requires matter dense enough to collide, radiation strong enough to ionize, gravity deep enough to compress, or motion fast enough to generate friction. It requires a star, or a planet near a star, or a moon near a planet massive enough to generate tidal forces, or a nebula thick enough to collapse under its own weight. These conditions are rare. The volume of space occupied by stars is negligible. The volume occupied by planets is smaller still. The volume occupied by atmospheres, by oceans, by surfaces warm enough to sustain liquid water, is vanishingly small. The corona paradox, the nebula's dual nature, the intergalactic medium's ghostly heat, the boomerang nebula's record cold. These are not anomalies. They are illustrations of the same truth. Temperature in the universe is not a spectrum. It is a scattering of islands, each one isolated, each one sustained by mechanisms that operate locally and do not extend beyond their immediate surroundings. The default state of the cosmos is not cold in the way a winter night is cold. It is the absence of the conditions that allow temperature to exist at all. Heat is the exception, the rare convergence of matter and energy in the same place at the same time, and it persists only as long as the conditions that created it remain in balance. Beyond the orbit of Mars, where sunlight weakens to a pale glow, the moons of the outer solar system drift through cold that would freeze carbon dioxide into frost in seconds. Europa receives about 25 times less sunlight than Earth. At that distance, the Sun is a bright star, nothing more. The ice crust encasing Jupiter's moon should be frozen solid, all the way to the core, a tomb of stillness measured in miles of ancient, motionless cold. Yet beneath that ice, an ocean larger than all of Earth's oceans combined stays liquid. The warmth does not arrive from above, it rises from within. Europa orbits Jupiter in an ellipse, not a perfect circle. As the moon swings closer to the giant planet and then farther away, Jupiter's gravity pulls and releases, kneading the interior of the moon like a hand-working dough. The rock and metal core flex. The ice shell bends. Friction becomes heat. Tidal heating, it is called, a name that sounds gentle but describes a process powerful enough to melt ice 10 miles thick and keep an entire ocean from freezing for billions of years. The surface temperature hovers near -260 degrees Fahrenheit. The ocean below, warmed by the grinding of gravity, remains liquid. No sunlight penetrates the ice. The ocean has never seen a star. Yet it persists, dark and deep, heated by the pull of a planet that never touches it. The ice shell itself tells the story. Cracks run for hundreds of miles across Europa's surface, ridges and fractures that map the stresses of a world being pulled in different directions with every orbit. Some regions show signs of recent resurfacing, places where liquid water may have welled up from below and refrozen into smooth plains. The surface is young by cosmic standards, renewed by the motion of the ocean beneath. The ice is not a static barrier, it breathes, it shifts. It cracks open and heals, over and over, as the moon flexes in Jupiter's grip. Europa is not alone. Farther out, in the realm of Saturn, the moon Enceladus drifts through a cold so profound that nitrogen would liquefy on contact. The moon is small, barely 300 miles across, a fragment compared to Earth's moon. Its surface is brilliant white ice, scarred and fractured, reflecting nearly all the dim sunlight that reaches it. For decades, scientists assumed it was geologically dead. Then Cassini arrived. The spacecraft approached the moon's south pole and found plumes, geysers of water vapor erupting from deep fissures in the ice, shooting hundreds of miles into space. Cassini flew directly through the plumes and tasted water, salts, and the building blocks of life. The instruments detected organic molecules, the kind that on Earth are woven into every living thing. Beneath the ice, another ocean. Beneath the ice, heat. Enceladus is even smaller than Europa, farther from the Sun, receiving even less light. Yet the same mechanism operates. Saturn's gravity pulls. The moon's orbit wobbles. The interior flexes. Heat rises. An ocean persists in a place where the sun's warmth is little more than a whisper. The plumes continue to erupt, feeding Saturn's outermost ring with fresh ice. The geysers vent thousands of pounds of water every second, a continuous exhalation that has likely persisted for millions of years. The ocean vents its warmth into the freezing void, and the void swallows it without acknowledgement. Yet the ocean does not freeze. The heat comes from within, generated by motion, by the relentless kneading of gravity across time spans longer than mountain ranges endure. The fissures at Enceladus's south pole have been named the tiger stripes, long parallel scars warmer than the surrounding terrain, glowing faintly in infrared. They are the warmest places on the moon, though still far below freezing by any terrestrial measure. Yet warm enough, relative to the rest of the surface, to mark the presence of an active interior, a reservoir of heat that has no connection to the distant sun. On Titan, Saturn's largest moon, the logic shifts, but the principle holds. The surface is cold enough to turn water into rock. Rivers carve channels through hills of frozen water ice. Lakes dot the polar regions, their shores mapped by radar from orbit. Seas spread across the northern latitudes, larger than the Great Lakes, deeper than many terrestrial reservoirs. But the liquid is not water, it is methane, it is ethane. Hydrocarbons that on Earth exist as gas, now flow as rivers, pool as lakes, evaporate into clouds, and fall again as rain. Titan is a world with weather, rivers, and seas, but where water is rock and methane flows like rain. The surface temperature rests near -290 degrees Fahrenheit. The Sun at this distance is a distant point of light, contributing almost nothing to the Moon's energy budget. Yet Titan has an atmosphere thicker than Earth's, a nitrogen sky laced with organic haze. Methane cycles through the air and across the surface in a hydrological system that mirrors Earth's water cycle, but translated into a vocabulary of cold. Clouds gather over the poles, storms sweep across the equator, riverbeds fill and empty with the seasons, each season lasting more than 7 Earth years. The largest sea, Kraken Mare, stretches longer than the Caspian Sea, a body of liquid methane and ethane, deep enough to drown mountain ranges. Radar soundings suggest depths of several hundred feet in some regions, a cold hydrocarbon ocean beneath a smoggy sky. Beneath the surface, scientists suspect another ocean, this one made of water, kept liquid by the same tidal heating that warms Europa and Enceladus. Titan may hold two kinds of ocean, one of methane on the surface, open to the sky, and one of water beneath the ice, hidden and warm, sustained by the flexing of the Moon's interior as it orbits Saturn. The methane on the surface should have been destroyed by sunlight long ago, broken apart by ultraviolet radiation into heavier hydrocarbons that settle as haze. Yet methane persists in the atmosphere, replenished by some process scientists are still working to understand. It may seep up from reservoirs beneath the crust. It may vent from cryovolcanoes, cold geysers that exhale methane instead of water. Either way, Titan is geologically active, driven by internal processes that have nothing to do with the faint warmth of the Sun. These are not planets warmed by their star. They are worlds heated by motion, by orbital mechanics, by the grinding of rock and ice under the grip of gravity. The Sun plays almost no role in their thermal balance. They could drift farther into the dark and remain unchanged. They could orbit a star that died long ago, and still harbor liquid water, still exhale geysers, still cycle methane through an atmosphere thick enough to hold weather. The cold of space does not determine whether a world can hold warmth. What matters is whether the world moves, whether it bends, whether it transforms motion into heat through the friction of its own existence. Europa, Enceladus, Titan. These are not edge cases, they are examples of a broader principle. Warmth in the universe does not require proximity to a star. It requires only matter, motion and time. A moon locked in orbit around a giant planet, flexing with each pass, can generate more sustained heat than a surface bathed in distant sunlight. The oceans beneath the ice of these moons may be older than the oldest ocean basins on Earth. They have never frozen. They have never seen light. They exist in total darkness, warmed by forces that operate independently of the Sun, sustained by a heat source that will persist as long as the moons continue to orbit, as long as gravity continues to pull. Scientists have sent probes through the plumes of Enceladus. They have mapped the ice shell of Europa with radar. They have watched methane rainstorms sweep across Titan's equator. The data suggests that the volume of liquid water hidden beneath the ice of the outer solar system may exceed the volume of all the water on Earth's surface. Most of it has never been touched by sunlight. Most of it exists in oceans that have no surface, no sky, no stars overhead. Just ice above, rock below, and in between, water kept liquid by the slow, patient grinding of a moon's interior, as it orbits a planet that itself orbits a distant, fading sun. These ocean worlds reframe the question of where warmth can exist. The habitable zone becomes only one possibility among many. A moon far beyond that zone, receiving a fraction of Earth's sunlight, can still harbor conditions that, on Earth, would be called temperate. The definition of habitable expands, not because the cold has retreated, but because the sources of heat are more varied than sunlight alone. The ocean beneath Europa's ice has been liquid for billions of years. It will remain liquid for billions more. The Sun will grow old, swell into a red giant, and consume the inner planets. Europa's ocean may still be there, warmed not by the dying star, but by the same tidal forces that have sustained it since the solar system was young. In the deep cold of the outer solar system, far from the light and heat of the Sun, these moons carry warmth within them. They do not borrow it, they generate it, they hold it. And in doing so, they remind us that the universe, for all its cold and all its emptiness, has carved out pockets of persistence, places where warmth endures, not because a star shines nearby, but because matter moves, and motion becomes heat, and heat becomes the quiet possibility of oceans that have never known a sunrise. The universe has offered thousands of worlds beyond our solar system, and among them, a growing list of candidates, sitting at just the right distance from their star. This distance has a name, the habitable zone, sometimes called the Goldilocks zone, where a planet orbits neither too close nor too far for liquid water to exist on its surface. Temperature becomes the filter through which the search for life must pass, the first gate in a series of gates, each one narrower than the last. Earth sits within the Sun's habitable zone, but only barely. Venus, closer in, is a furnace beneath clouds of sulfuric acid. its surface hot enough to melt lead. Mars, farther out, is a frozen desert, where the atmosphere has thinned to almost nothing and water, if it exists at all, hides beneath ice or locked in minerals. The habitable zone is not a wide band, it is a narrow ribbon, and Earth threads it, bracketed on both sides by worlds that failed the temperature test in opposite directions. The zone shifts depending on the star. A red dwarf, smaller and cooler than the Sun, casts its habitable zone much closer in, so close that a planet there might orbit its star in a matter of days rather than a year, locked in a tight embrace, where one face may always point toward the light and the other toward eternal night. A massive blue star, burning fierce and brief, pushes the zone outward, but offers little time for life to take hold before the star exhausts itself. Every star draws its own ring of possibility, and every ring is different in width, in distance, in duration. Finding a planet in the habitable zone is only the beginning. Distance alone does not guarantee warmth. A planet needs an atmosphere thick enough to trap heat, but not so thick it becomes a runaway greenhouse like Venus. It needs geological activity to recycle carbon and maintain that atmosphere over billions of years, pulling carbon dioxide from the air and locking it in stone, then releasing it again through volcanoes in a slow planetary breath. It needs a magnetic field to shield the surface from the solar wind that would otherwise strip the air away, molecule by molecule, until nothing remains but bare rock under radiation. Temperature is the filter, but it is not the only one. The search has become a matter of light. A telescope that can taste the air of a world 100 light-years away now orbits the Sun, far beyond the interference of Earth's atmosphere. The James Webb Space Telescope watches distant planets as they pass in front of their stars, and in that brief transit, starlight filters through the edge of the planet's atmosphere. Different molecules absorb different wavelengths. Water vapor leaves a signature in the infrared, carbon dioxide leaves another. Methane, oxygen, ozone, each one imprints itself on the light, and the telescope reads the spectrum like a recipe, cataloging the ingredients of alien air without ever seeing the world itself. Temperature can be inferred from this light. A world too hot boils its water into steam and the spectrum shows it, the atmosphere thick with vapor, the surface hidden beneath a permanent haze. A world too cold locks its water in ice, and the atmosphere thins, the signal fading to almost nothing. The telescope does not see the planet's surface, it does not need to. The air tells the story, and the story is written in the wavelengths that survive the crossing. 40 light-years away, a small red dwarf star hosts 7 planets, all of them close enough to fit within the orbit of Mercury if they circled our Sun. The star is called TRAPPIST-1, named for the telescope that first detected the worlds around it. 3 of those planets sit in or near the habitable zone. They are roughly the size of Earth. They are made of rock. They receive enough starlight to allow liquid water, if conditions align, if the atmospheres are thick enough, if the chemistry is right. No one knows yet if those planets have atmospheres. No one knows if they have oceans or ice sheets or barren plains of stones scorched by flares from their restless star. The James Webb Space Telescope has begun to study them, filtering their light, searching for the telltale absorption lines of water, carbon dioxide, anything that might hint at weather, at chemistry, at the possibility of something more than rock and radiation. The data arrives slowly. Each transit is a narrow window, a few hours when the planet crosses the star, and the light passes through a thin shell of air at the edge of the world. Each spectrum is a whisper, and the noise is loud, and the signal must be extracted from dozens of transits, stacked and averaged until the pattern emerges. The search has revealed a pattern across the thousands of known worlds. Rocky planets are common. Planets in the habitable zone are less common, but not rare. Planets with atmospheres thick enough to hold heat are rarer still. Planets with the right kind of atmosphere, stable over geological time, with active geology and a magnetic field and an orbit that does not wobble too much, these are the true anomalies, the needles in a haystack the size of the galaxy. Earth is one of them. It orbits at a distance where water stays liquid across most of the surface, where ice forms only at the poles and in the high mountains, where the oceans cover more than 2/3 of the world. It has an atmosphere dense enough to trap warmth, but transparent enough to let sunlight through, a balance maintained by the presence of life itself, by the oxygen exhaled by plants, and the carbon dioxide absorbed by them in return. It has a molten core that generates a magnetic field, shielding the surface from the solar wind that stripped Mars bare billions of years ago. It has a large moon, born from a collision early in the solar system's history, that stabilizes the tilt of its axis and smooths the seasons. It has plate tectonics, a slow churn of crust that recycles carbon and regulates the greenhouse effect over millions of years. Each of these factors is necessary. None of them is guaranteed. The habitable zone is not a promise. It is a starting point, a line drawn in space marking where the equations allow liquid water to exist if everything else goes right. A planet can sit at the perfect distance and still freeze if its atmosphere is too thin, if the greenhouse effect is too weak. It can sit at the perfect distance and still boil if the greenhouse effect runs away, if volcanic outgassing floods the air with carbon dioxide faster than the rocks can absorb it, if the oceans evaporate and the water vapor itself becomes a greenhouse gas, trapping more heat until the surface glows. Distance sets the range of possibility, but the outcome depends on a cascade of conditions, each one contingent on the last. The James Webb Space Telescope will continue to watch. It will catalog atmospheres around dozens of worlds in the coming years. It will measure temperatures by reading the glow of their day sides and the darkness of their night sides. It will search for oxygen, for methane, for the chemical imbalances that might hint at life, at metabolisms that alter the air in ways that geology alone cannot explain. The search is patient. The distances are vast, and the signals are faint, and the work will take decades. Among the thousands of known worlds, only a handful sit in the narrow band where liquid water could exist. Among those, only a fraction have been studied closely enough to know anything about their air. Among those, none has yet shown the unmistakable signature of life. The search continues, transit by transit, spectrum by spectrum. Temperature is the filter, but it is also the product. A planet does not simply receive warmth from its star and hold it passively. It must capture it, regulate it, balance it across billions of years through the interplay of atmosphere and ocean and rock, and on Earth, life itself. The warmth experienced on the surface is not a given. It is the result of a magnetic field that has persisted for 4 billion years, a recycling crust that has kept the carbon cycle running, a stable orbit that has not been perturbed by passing giants, an atmosphere balanced by forests and plankton and bacteria in the soil. Strip away any one of these and the warmth fades. The habitable zone is a ribbon in space, drawn around every star, marking the distance where warmth is possible. But possibility is not the same as presence. The search for habitable worlds is a search for the rare exceptions, the places where distance and chemistry and time have aligned in just the right way, where the equations permit warmth, and the warmth has lasted. Earth is one of those exceptions. It sits in the zone, it holds the warmth. It has done so for billions of years, long enough for life to emerge, to spread, to alter the atmosphere and stabilize the climate. and become part of the system that maintains the conditions for its own survival. Earth hangs in space at an average temperature near 15 degrees Celsius. Not hot, not cold, comfortable, temperate. A world where water flows in 3 states at once: ice caps at the poles, liquid oceans spanning most of the surface, vapor rising into clouds that circle the globe. This warmth is not a gift from the sun alone. Strip away the atmosphere and Earth freezes. The warmth we take for granted is a product of a chain of coincidences that took billions of years to align. The greenhouse effect wraps the planet in a thermal blanket. Carbon dioxide, water vapor, methane, gases that trap outgoing heat and hold it close to the surface. Without them, Earth's average temperature would fall to roughly 18 degrees below 0 Celsius. The oceans would lock into ice, the rivers would stop, the rain would cease. The difference between the world we know and a frozen stillness is a thin veil of gas, maintained by processes so interwoven that removing any single thread unravels the whole. Plate tectonics recycle carbon, continents drift, seafloor spreads, volcanoes exhale carbon dioxide back into the air, balancing what the oceans and rocks absorb. This cycle has run for billions of years, neither too fast nor too slow, keeping the greenhouse effect stable enough for liquid water to persist. A world without plate tectonics, like Mars, like Venus, loses this thermostat. The atmosphere either bleeds away or runs into a feedback loop that never stops. Earth's crust breaks into pieces that slide and collide and sink back into the mantle, carrying carbon with them, releasing it again through volcanic vents. The cycle is slow, planetary, patient. It has kept the surface habitable not for centuries but for eons. A magnetic field shields the atmosphere from the solar wind. Charged particles streaming from the sun could strip away the gases that hold the warmth, given enough time. Mars lost its magnetic field early in its history. Its atmosphere thinned, its surface froze. Earth's molten iron core still churns, generating a protective bubble that reaches tens of thousands of kilometers into space. The field is invisible, but without it, the air itself might have vanished long ago. A large moon stabilizes the axial tilt. Earth's rotational axis tips roughly 23 degrees relative to its orbit. This tilt gives the planet seasons, predictable, cyclical, mild enough for ecosystems to adapt. Without the moon, the tilt would wander over millions of years, swinging from near zero to extreme angles, plunging the planet into chaotic climate shifts. The moon itself formed from a collision early in Earth's history, a violent accident that happened to leave behind a stabilizing companion. A Mars-sized body struck the young Earth, vaporized itself and a portion of the crust, and from the debris a moon coalesced. That moon now holds the planet's spin steady, a gravitational anchor preventing the slow tumble that would make the climate unrecognizable over geological time. An orbit in the habitable zone places Earth at just the right distance from the Sun. Too close and water boils away. Too far and it freezes permanently. Venus sits inside this zone, but runaway greenhouse heating turned its surface into a furnace. Mars sits near the outer edge but lost its atmosphere and froze. Earth threads the needle, and even then it required every other factor – atmosphere, magnetic field, tectonics, the moon – to maintain the warmth. The zone itself is narrow. A shift of a few million kilometers in either direction, and the story changes. The universe is 13.8 billion years old. Complex life on Earth required roughly 4 billion years to emerge. Single-celled organisms appeared relatively quickly, but the leap to multicellular life, to ecosystems, to creatures that could regulate their own temperature and move and think, that took the better part of the planet's entire history. Warmth alone is not enough. Stability is required. Time is required. And time, in a universe where stars burn out and galaxies drift apart, is not infinite. The sun will not shine forever. In a few billion years it will swell into a red giant and consume the inner planets. The warmth Earth enjoys now is temporary, bounded on both ends by cold. The overwhelming majority of space is not just cold, it is empty, dark, and silent. The voids between galaxy clusters stretch for hundreds of millions of light-years, containing almost nothing. No stars, no planets, no gas clouds dense enough to collapse into new suns. Even within galaxies, the space between stars is vast. The nearest star to the Sun lies more than 4 light-years away. If the Sun were the size of a marble, that star would be another marble more than 600 kilometers distant, with nothing but vacuum in between. Most of the matter in the universe is not on planets, it is not in stars. It is in the thin gas threading the space between galaxies, so diffuse that a handful of it would contain only a few atoms. In the halos of galaxy clusters, this gas can reach temperatures of millions of degrees, heated by the gravitational collapse of matter on the largest scales. Yet it is so sparse it would register as a near-perfect vacuum in any laboratory on Earth. Hot by measure of particle speed, but empty. Unable to warm anything. A thermometer placed in that gas would not register heat. There are too few particles to transfer their energy. The coldest natural place ever found is not in the depths of intergalactic space. It is the Boomerang Nebula, a dying star exhaling so fast the gas chills below the background of space itself. The temperature there falls to roughly 1 Kelvin, colder than the faint microwave glow that fills the rest of the universe. A star at the end of its life, pouring out its remaining material in a final breath, and in doing so, creating the only known region of the cosmos that has cooled below the ancient afterglow of the Big Bang. The gas expands so rapidly it loses energy faster than the surrounding radiation can replace it. Warmth is not the default state of the universe, it is the exception. A star ignites and for a time, millions or billions of years depending on its mass, it radiates heat into the surrounding void. Planets form in the disk of debris around it. A few might fall within the narrow band where liquid water can exist. Fewer still will have the right mass to hold an atmosphere, the right chemistry to build a magnetic field, the right orbital companions to stabilize their climates. And among those, only a fraction will maintain that balance long enough for life to take hold. Earth required a magnetic field, a large moon stabilizing the axial tilt, plate tectonics recycling carbon, and an orbit in the habitable zone simultaneously. A list of coincidences, each one necessary, none of them guaranteed. Remove any single element, and the story changes. The warmth fades, the water freezes or boils away. The atmosphere thins, the surface becomes hostile. The fact that all these conditions aligned here, on this world, at this time, is not evidence of design, but of rarity. Countless worlds exist where one or more of these pieces is missing. They are frozen, or airless, or geologically dead, or bathed in radiation, or locked in tidal resonance with their star, one face always burning, the other always frozen. There are ocean worlds in the outer solar system, Europa, Enceladus, that maintain liquid water not through sunlight, but through internal heat. Tidal forces from their parent planets knead their interiors, generating friction, melting ice from below. Europa receives about 25 times less sunlight than Earth, yet beneath its ice, an ocean larger than all of Earth's oceans combined stays liquid. These moons are warm in the dark, heated by gravity rather than radiation. But their warmth is hidden, buried under kilometers of ice, isolated from the cold above and the cold beyond. Cassini flew directly through the plumes erupting from Enceladus and tasted water, salts, and the building blocks of life. Titan has lakes and seas, rivers and rain. weather systems that shape its surface. But the liquid is methane, not water. The temperature hovers near -180 degrees Celsius. Water on Titan is as hard as granite. Methane plays the role water plays on Earth, cycling through the atmosphere, carving channels, filling basins. A world with weather, rivers and seas, but where water is rock and methane flows like rain. The search for other habitable worlds scans thousands of stars. Planets have been found orbiting many of them, thousands of worlds beyond our solar system. And among them, a growing list of candidates sitting at just the right distance from their star. Some are roughly the right size. Some show signs of atmospheres, but distance is only one variable. Atmosphere, magnetic field, geological activity, orbital stability. Each one filters the list further. A telescope that can taste the air of a world 100 light-years away can tell whether water vapor is present, whether carbon dioxide exists, whether methane might hint at biological processes. But it cannot tell whether that world has a magnetic field, or a stabilizing moon or plate tectonics, or any of the other threads that hold Earth's warmth in place. Even if another world holds liquid water, even if it sits in the habitable zone, even if it has an atmosphere and a magnetic field, there is no guarantee it will stay warm. Climate systems are fragile. Feedback loops can spiral. A planet can freeze or overheat, tipping into a state from which it never recovers. Earth itself has come close. Periods of near-total glaciation, periods of extreme heat, but it has always returned to balance. That resilience is not a given. It is the result of specific conditions, specific feedbacks, specific accidents of formation and evolution. The universe is mostly cold because it is mostly empty. Temperature requires matter, and matter is rare. The stars that generate heat are scattered across unimaginable distances. The planets warmed by those stars are rarer still. The planets that maintain that warmth long enough for complexity to arise are the rarest of all. Earth is warm, not because warmth is common, but because a series of unlikely events converged in one place at one time and held steady for billions of years. The magnetic field endures. The moon remains. The tectonics continue. The orbit holds. The atmosphere persists. Each one a thread in a net that keeps the cold at bay. Everywhere else, the cold waits. Not as an active force, but as the baseline. The natural state. The condition to which everything returns when the temporary sources of heat, stars, gravitational friction, radioactive decay, finally run out. Warmth is the anomaly, the brief flicker, the exception that must be explained, maintained, protected. And here, on this one world, in this one corner of one galaxy, among hundreds of billions, warmth has persisted long enough for oceans to form, for continents to drift, for life to emerge and diversify, and look outward at the cold, and ask why it is so. Somewhere between the sun's surface and the cosmic background, the physics turns strange. The heat radiating from our star does not thin gradually, like warmth fading down a hallway. It vanishes almost completely the moment it leaves the grip of matter. And in that vanishing, a truth emerges that reshapes the way we see warmth itself. The sun's core burns at 15 million degrees Celsius. The surface, cooler but still ferocious, glows at 5,500 degrees. And then, inexplicably, the corona, the sun's outer halo, burns hotter than the surface itself, reaching temperatures of 1 to 3 million degrees. It is a puzzle scientists still debate, a reversal of expectation written in plasma and magnetic fields. The corona shimmers like a crown of fire, defying the logic that heat should diminish with distance from the source. No consensus explains it fully. The sun, even after centuries of study, holds its secrets close. But step beyond the corona, beyond the last wisps of solar wind, and the numbers collapse. The average temperature of space, measured not by matter, but by the faint radiation filling every corner of the universe, sits at 2.725 Kelvin. That is just 2¾ degrees above absolute zero, the floor of the universe, a temperature nothing has ever actually touched. The gap between the Sun's surface and the void surrounding it is not a gradient, it is a cliff. The reason lies in what temperature truly is. Temperature measures the average kinetic energy of particles, atoms and molecules jostling, colliding, vibrating. In a gas, in a liquid, in a solid, that motion translates to heat we can feel. But in a vacuum there is almost no matter, no particles to carry kinetic energy, no medium to hold warmth. Temperature requires matter to exist. In a vacuum, the question itself barely makes sense. A freezer chills you through air pressing against your skin, molecules conducting cold into your body. Space has nothing to press against anything. The 2.725 Kelvin background is not the temperature of emptiness, it is the temperature of the cosmic microwave background, the oldest light in the universe, still traveling, still cooling. Photons carry it, not atoms. It is the afterglow of creation, stretched thin across 13.8 billion years of expansion. Heat moves in three ways. Conduction requires direct contact, particle to particle. Convection requires fluid or gas in motion, carrying warmth in currents. Both demand matter. Both fail in a vacuum. Only radiation remains. Heat transferred through electromagnetic waves through light itself. The Sun's energy crosses 93 million miles of nothing in 8 minutes, carried not by any substance but by light. Infrared, visible, ultraviolet, all streaming outward at the speed of light, indifferent to the void. The Sun emits more energy every second than humanity has used in all of recorded history. And almost all of it pours into emptiness. An astronaut floating in low Earth orbit experiences this isolation firsthand. In direct sunlight, exposed metal on a spacecraft can reach 250 degrees Fahrenheit. The same surface in shadow drops to roughly -250 degrees. Step from sunlight into shadow, and the temperature swings more than 300 degrees in seconds on the same body. The International Space Station experiences 16 sunrises every single day, 16 full swings between furnace and freezer. The metal skin of the station expands and contracts, groaning under thermal stress that would shatter most materials. NASA spacesuits manage this extremity, with 18 layers of insulation and a network of water-cooled tubes against the skin. The astronaut inside floats in a controlled microclimate, a bubble of Earth wrapped around flesh and bone. Without it, the body would not freeze instantly. There is no air to conduct heat away. Instead, the astronaut would radiate warmth slowly into the void, cooling over minutes, not seconds. In direct sunlight, the skin facing the Sun would blister while the shadowed side chilled. The vacuum does not kill with cold, it kills with contradiction. This is the paradox at the heart of space. The Sun blazes. The void does not absorb that heat, it simply refuses to hold it. Warmth exists only where matter gathers, only where particles can collide and transfer energy. Everywhere else, the universe defaults to cold. And cold, in the cosmos, is not uniform. The same nebula, a cloud of gas and dust, nursery of future stars, holds pockets of 10,000 degrees, and pockets of nearly absolute zero, separated by light years. The thin gas threading between galaxies can reach millions of degrees, heated by shock waves from colliding galaxy clusters, yet it is so sparse it would register as a near-perfect vacuum in any laboratory on Earth. Temperature and density decouple. A gas can be scorching and empty at once. The coldest natural place we have ever found sits 5,000 light-years away. The Boomerang Nebula, a dying star exhaling so fast the gas chills below the background of space itself, reaches temperatures near 1 Kelvin, colder than the cosmic microwave background, colder than the universe around it. The star's final breath, racing outward, cools by expansion, dropping below the faint warmth that fills the rest of creation. It is the only known place where nature has beaten the ambient temperature of space without human intervention. And yet, even in this cold, warmth persists in hidden pockets. Europa, a moon of Jupiter, receives about 25 times less sunlight than Earth. Its surface is a shell of ice kilometers thick, locked in permanent freeze. But beneath that ice, an ocean larger than all of Earth's oceans combined stays liquid. The heat comes not from the sun but from within. Tidal forces from Jupiter's gravity, kneading the moon's interior, friction generating warmth in the deep. Enceladus, a moon of Saturn, erupts geysers of water vapor from cracks in its south pole. Cassini flew directly through the plumes and tasted water, salts, and the building blocks of life. Heat from tidal flexing, not sunlight, keeps the ocean liquid. Titan, another moon of Saturn, has weather, rivers and seas, but where water is rock and methane flows like rain. Surface temperature hovers near -290 degrees Fahrenheit, yet the moon is geologically active, its atmosphere thick with organic haze. These ocean worlds prove that warmth in the solar system does not require proximity to the sun. It requires only energy, and energy can come from gravity, from radioactive decay, from the slow grinding of planetary interiors. The search for life beyond Earth hinges on this understanding. The habitable zone, the range of distances from a star where liquid water could exist on a planetary surface, is a first filter, a rough sketch of possibility. Earth sits within the Sun's habitable zone, but only barely. Venus, closer, became a furnace. Mars, farther out, lost its atmosphere and froze. The margin is narrow. Thousands of worlds beyond our solar system have been confirmed, and among them, a growing list of candidates sitting at just the right distance from their star. The James Webb Space Telescope can taste the air of a world 100 light-years away, analyzing starlight filtered through an exoplanet's atmosphere as it transits its star. Temperature, chemistry, the presence of water vapor or methane, all inferred from the spectrum of light. The TRAPPIST-1 system, 40 light-years distant, holds 7 Earth-sized planets, at least 3 in or near the habitable zone. Whether any of them hold liquid water, whether any harbor life, remains unknown. But the overwhelming majority of space is not just cold, it is empty, dark, and silent. The universe has been cooling for 13.8 billion years, and it is not finished. The cosmic microwave background, once the searing light of the early universe at 3000 Kelvin, has stretched and dimmed to 2.725 Kelvin. Expansion will continue. The background will cool further. In trillions of years it will approach absolute zero, and the universe will be darker still. Warmth, then, is not the default state of the cosmos. It is the exception, the anomaly, the result of matter gathering and energy concentrating in rare and temporary configurations. Stars burn for millions or billions of years, but the universe is older than most stars and will outlast all of them. Planets with atmospheres and liquid water are vanishingly rare. Life, rarer still. Earth's average surface temperature sits near 15 degrees Celsius, maintained by a greenhouse effect, liquid oceans, a magnetic field, and plate tectonics acting together. Strip away the atmosphere and Earth freezes. The warmth we take for granted is the product of a chain of coincidences that took billions of years to align. A magnetic field generated by a molten core. A large moon stabilizing the axial tilt, preventing wild climate swings. Plate tectonics recycling carbon, regulating the greenhouse effect over geological time. An orbit in the habitable zone. Each one necessary, none of them guaranteed. Complex life on Earth required 4 billion years to emerge. 4 billion years of liquid water, of stable temperatures, of chemistry iterating in tidal pools and deep-sea vents. The universe is 13.8 billion years old, but most of it has never known warmth. Most of it never will. The verdict, then, is not that space is cold. It is that warmth is rare. Warmth requires matter, energy, and time, all converging in the same place. It requires gravity to gather gas into stars, fusion to ignite them, planets to form in the narrow band where water stays liquid, atmospheres to trap heat, and geology to sustain it. Every warm place in the universe is a conspiracy of physics, a list of coincidences stacked so high that the existence of any one of them feels like a miracle. We live on a world where warmth is ordinary, where the air holds heat and the ground radiates it back, where the sun rises every day and the temperature swings are gentle. But step outside that thin envelope of atmosphere, beyond the magnetic field, past the orbit of the moon, and the universe reverts to its natural state. Cold, empty, indifferent. Warmth is not the texture of the cosmos. It is the exception we cling to, brief and fragile, a flicker against the void. The universe has been cooling for nearly 14 billion years, and it is not finished. The cosmic microwave background, that faint afterglow filling every corner of space, grows colder with every passing second as the fabric of the cosmos stretches. Today it rests just 3 degrees above absolute zero, the floor of the universe. A temperature nothing has ever actually touched. Warmth is not the default, it is the exception. Strip away the atmosphere, and Earth freezes. The heat we take for granted is the product of a chain of coincidences that took billions of years to align. A magnetic field, a large moon stabilizing the axial tilt, plate tectonics recycling carbon, an orbit in the habitable zone. A list of necessities, none of them guaranteed. The overwhelming majority of space is not just cold, it is empty, dark, and silent. And in that silence, warmth becomes the rarest thing in the cosmos. A brief flicker, a local rebellion against the long descent towards stillness.